Okay, let's get started. So, we've been talking about Liouville's theorem and the special case of when we have the differential inclusion into just the rotations and the quantitative generalization of that statement by Friesecke James Muller, right? And now we're going to discuss a result that is a much weaker quantitative generalization of Liouville's theorem, and that's the theorem by Muller, Sverak, and Yan. All right, so how does this go? Suppose we have a sequence UN, UK belong to W1 n over 2, omega into Rn. Omega is in Rn, of course. So we'll write that here. N is even, and n is bigger than or equal to 4. There's similar hypothesis to the ones we've been discussing, that the gradient is forced closer and closer to a set of matrices, but this time it's the conformal matrices, which, as people know, is just the distance, it's just the rotations times a constant. And the sequence tends weakly in the Sobolev space to this limiting function, right? Which means the gradients converge weakly in L n over 2, and the functions converge strongly, right? Then, good. We firstly have that the gradients actually converge strongly in LP. For P between 1 and strictly less than n over 2. And as a consequence, the U belongs to the conformal matrices. Okay. So at this point we understand very well that having the gradient getting closer and closer to a set of matrices in no way guarantees that the gradient of the limiting function, when we take the weak limit, is going to be inside that space of matrices, right? This is hopelessly false if you have a rank 1 connection inside the set where the segment formed by this rank 1 connection is not completely contained within the set. And generally it is hard to prove. It is hard to prove that the limiting function is inside the set of matrices that you're forcing the sequence to get closer and closer to. We talked about Sverak's theorem that if we are in 2 by 2 and we have a set K which is got no rank 1 connections and is connected and is closed, then it's true, but that's a very special property of 2 by 2. This is for any n. The set of conformal matrices is indeed a set without any rank 1 connections. It's actually a linear subspace without any rank 1 connections. And but we can't apply Sverak's theorem because we are in any dimension or any even dimension. And this requires quite different techniques, quite a lot of different work. This is the main theorem of one of the other papers of the three that I want you guys to collectively or individually read and present on. This is a relatively short and neat paper. And let's see in what sense this is a quantitative generalization of Liouville's theorem. So what was the structure of Friesecke James Muller theorem? So Friesecke James Muller was that if we have that the distance, the power p of the gradient away from rotations was of order epsilon, then with the same control we actually have that the distance away from some fixed matrix inside the rotations is less than a constant times epsilon. So the hypothesis of an order epsilon and the conclusion is also of order epsilon, right? We have an optimal conclusion. We can't possibly do better than this because we have the same epsilon occurring in the hypotheses and in the conclusion, right? And I sketched that if we are willing to, if we do this by hand with elementary methods, we can get some kind of result with a root power of epsilon, but the real surprising thing here is that we don't lose anything with this conclusion. So that's Friesecke James Muller. And now I would like to say something similar, except we're replacing rotations with conformal matrices. So suppose we have a sequence satisfying this hypothesis. Okay. Then, so in my statement of this theorem, I've taken the sequence to be converging weakly, right? But if we have just an arbitrary sequence satisfying this, so I suppose, let's call this thing star. UK satisfies star. Then we can pick a subsequence that does converge weakly. Let's separate this stuff off. And then just applying the theorem to this subsequence, we have that the limiting function is a conformal matrix, is inside the conformal matrices. And by other theorems, the rigidity result of Liouville does hold true. This is another deep theorem by Iwanik and someone else. I think it's Gavin. So this guy is a Mobius mapping in the sense that we discussed before. And that's a highly non-trivial thing. So in the case when we have a smooth function, then that's Liouville's theorem. But all we know about the limiting function is that it is in Sobolev space, W1 n over 2. But it is nevertheless true. So I should say this is a deep theorem, a deep and fairly recent theorem, a deep, difficult and recent theorem. And we have that the gradients are converging strongly in something just a bit less than n over 2. So here we have the initial hypothesis in sort of epsilon and the conclusions in terms of epsilon. Here we have to extract the subsequence, right? But we have that the gradients are tending close to this thing that is rigid, because we know that Ux is this thing that is the composition of the inverse, the inversion mapping. So it's going to be X minus A like this, times a reflection which I'm going to call Q times an affine mapping A, right, where I of x is x over mod x squared, reflection to the sphere. So this is a very specific thing, this gradient. It is not like in this statement just a fixed matrix. It is something that actually is moving, right? It's not fixed for every x, but it's very controlled because these mappings are extremely controlled. These are just inversions through the sphere times a reflection times a affine map whose gradient is conformal, right? So it's a similar conclusion from the fact that we are close to an arbitrary large set of matrices. We force the gradient to be close to a very specific thing, Yeah? So in this statement, we're close to a large set of matrices, rotations, and we force the gradient to be close to just one fixed guy. Yeah? In this statement, we are close to an even larger, much larger set of matrices, right? All linear, all scalar multiples of rotations, and we force it to be close to a specific function whose gradient is not affine, but it's very defined. All these Mobius mappings are very, very defined. They're complete. This is a completely concrete description of what this mapping is. Is it clear how these statements are related? Yeah, so this is the Liouville theorem that I talked about. So this is Liouville 1851, that if you, I think I said C3 from omega into Rn, the differential conclusion. I think it might have been your question as well at the time about the regularity here, right? Then this implies that U is Mobius in this sense. And at the time you asked, I think it was you, about do we need this C3? And I started talking about that actually we need less. We could have C1 with something like a similar proof, but to actually go further, to have a weaker regularity, we now know about this concept of Sobolev space. We know about the concept of weak derivatives. So we can ask, can we do this when we have just one? We just have a weak derivative, so it doesn't even exist pointwise, and so that would be replacing it with this hypothesis that we're in W1Q for some Q. Yeah? If Q is less than n over 2, there are counterexamples, right? So it's false for n over 2 if we are even, in even dimensions. But if we are in n over 2 and n is even, then the conclusion still holds true. And that's what I meant by this. This is the deep theorem of Iwanek. And for odd, yeah, it's an unknown problem, and it's a very well-known problem. That's exactly the kind of problem I like. So this is an extremely elementary statement. Right? This is something that I should make sure that this is clear. Even and this, then use Mobius. This is something that anybody can understand, and it's it's as far as you can push this. This is the all right. So one of our best concepts of having a weak derivative at the moment is Sobolev space, and within that scale, this thing is an optimal theorem. That's as good as it gets. And for odd n, establishing that would be great. And that's a long-time open problem. That would be an incredibly good. You'd be very famous if you solve this problem because everybody can understand this question. There's been for a long time, people have been trying to reduce the regularity required to do this statement, and that's completely resolved in even dimension, but for odd dimension it isn't. And actually, this theorem is a kind of, I won't exactly say it's a generalization because I think it uses this, but we have exactly the same level of regularity that we have this n over 2, and the statement is false of this theorem unless we have n over 2. Yeah, that's why in this part of the statement we have that the gradient is actually close to this thing that is very, very tightly controlled. Yeah? And obviously we can't do any better because we do have differential inclusions into the conformal matrices that are not affine. So this is absolutely part of the truth of the situation. But this is massively weaker than this, right? So this is information of order epsilon, the conclusions of order epsilon. This statement is this statement is that we have, this is getting close down to 0, so we can put the error as being equal to, say, epsilon k, but we don't have any control of this thing in terms of epsilon k, right? We're just saying that if this is small, then this is also small, right? So there isn't even any root power, there's just nothing, right? It's just if the hypothesis is that we have something small, then the conclusion is that we have something small, but we have no control on the how small in the conclusion in terms of how small in the hypothesis. Yeah? Okay, is the statement clear? Is the point of this clear? Thumbs up if you are happy with this, thumbs down if not. This is for my mind a very nice theorem, a very cute theorem. But obviously there's a lot to be understood about how well you can have an analog of Muller's Friesecke James Muller quantitative regularity theorem when you expand the set of matrices to be the full conformal set. If you don't have the full conformal set, there is actually a much stronger result, and that's by Farako and Zong, and that's another fairly recent result, which is that if you have a set, let's call it pi, contained within the conformal matrices, and then pi is compact, and pi does not include 0, then you have a theorem of the order of Muller that you can replace this thing by pi. You can have this conclusion replaced by pi, and then you'll have that this thing is less than, is close to some the phi where is Mobius. So it's the full strength. You have epsilon in the hypotheses, and you have epsilon in the conclusion, but you are taking a smaller subset of these things, of the conformal matrices. And but this too is a lovely theorem, and it follows the strategy of Friesecke James Muller, but there's many more technical complications to push this through. Okay, so if you like this theorem, then this is one of the papers you can choose to read and present. That's what you guys have to decide. So my goal over the next few classes is to get to the point where I can explain the statements of the 3 theorems and the 3 papers I'm suggesting for you, and so that you can choose and you have time to read and prepare. Okay, so that is one of them, and this is the paper by Muller-Sverak-Yan. I really hope I spelled that right. And I fear it might be just like this, but okay, we'll find out later. Yeah, it's a short paper, it's 10 pages, but it uses some things that you maybe don't know you'll have to learn about, called quasi-convexity. Okay, so now let's talk about the other paper, which I already mentioned, which is the Sverak paper proving compactness. Right? So this was the theorem of the end of last class, that if we have a set, let me just maybe state it, that if we have K contained within 2 by 2, closed, connected, and no rank-bound connections, then if we have a sequence such that we are forcing the gradients to be closer and closer to k, then actually the gradients converge strongly to the weak limit. So that's it. Say, and UK is tending weakly in W1P to U, then actually it's tending strongly. The gradients are converging strongly. So weak convergence goes to strong convergence. This is one of the simplest to state, easiest to understand instances of compensated compactness. The structure of the set of things we're forcing the gradient to be close to is improving weak convergence into strong convergence. Okay, there is another cool thing proved via these techniques in Sverak's paper, and that's what I'm about to explain. And that is that we can generalize this basic fact we learned from complex analysis, that the differential inclusion into the conformal matrices in 2 by 2 gives us analyticity. So this is one of the first things we learn in complex analysis, and it's one of the things I emphasize. I call it the first theorem of complex analysis. So from complex analysis, if we have U, which is going from some region omega inside the complex numbers to the complex numbers, and it is one-time differentiable. So, and U is differentiable on omega, then U is analytic. Okay, and well, several of you did complex analysis in my class, so hopefully you are very clear on this, because we did this formulation, we talked about this a number of times, and that just follows because if we have a function that's holomorphic and it's one-time differentiable, then let's call it not U, because we typically use U in the Cauchy-Riemann equations, call it F, because if we write this in the standard way, then we have that being one-time differentiable exactly means we satisfy the Cauchy-Riemann equations. All right. This is minus v of x. Yeah. And my claim, or what I told you, is that satisfying the Cauchy-Riemann equations, if we reformulate this just as a function from R2 to R2, that's exactly the same as being inside the conformal matrices. Is that familiar? Does that come back to you people? Yeah? Cool. But what are the hypotheses here? The hypotheses are that we have something that is one-time differentiable. Okay? So there's a pointwise derivative that exists everywhere. Yeah? That is a very that's quite a strong property. The whole reason that the notion of Sobolev space exists is that lots of situations, lots of applications, we're taking limits of something and we want to pass the limit with our sequence of functions, and we're not necessarily going to have the limit function have pointwise derivatives. That's the example I showed you. The limit of C1 functions isn't necessarily going to be C1. So we would like to have an analog of this where we don't insist on having pointwise derivative. Instead, we have just a Sobolev function whose gradient belongs to this set of matrices, the conformal matrices, and would like to conclude that it's analytic. And we actually can. And I'm going to sketch that to you. And the other main theorem in the Sverak paper, which proves this, is a generalization of this, that instead of just taking conformal matrices, we can take a much larger set of, we can take a very large set of, we can take a wide class of sets of matrices, which are sets which obviously have no rank 1 connections, or that would be false, but are also elliptic in a certain sense that I'll explain. So that's where this is going. We're going to talk about a generalization of this elementary statement from complex analysis to where the hypotheses are that the functions inside Sobolev space, and then I'm going to state Sverak's theorem and say why it's interesting. Okay, coming up. Okay, so recall we did a couple of proofs of the special case of Liouville theorem when we do the differential inclusion into rotations to show that it's actually affine. We did one proof on the hypothesis where we had invertibility, right? And then there was this triangle that we did that was mapped to a triangle because distances had to be preserved. And we did a more modern proof that used different things, right? So we're going to use some of those ideas to show the following. So suppose, and it's also a nice introduction to some concepts that are pretty important. So suppose we have U belonging to W1P from omega in R2 into R2, and we have that du belongs to the conformal matrices. No? Then U is C infinity. This is what we're going to show, and this I claim. So I was going to say that this is a generalization of the classical theorem from complex analysis, but that's not actually true. The hypothesis of being pointwise differentiable is not implied by is a completely different class than this. So there are functions that are pointwise differentiable that are not actually in Sobolev space, which is kind of surprising initially. So there are functions that are pointwise differentiable whose derivative is unintegrable in the Lebesgue sense. So they're not in Sobolev space. So it's not the case that this is a generalization of the classic theorem of complex analysis. It's a reformulation to a broader class. It's a reformulation to a different class of mapping, a different class of mappings that are actually more useful. So the space of functions that are pointwise differentiable is not that useful a class of mappings, but it isn't a priori also a particularly nice class of mappings, because as I say, you can have functions that are pointwise differentiable whose gradient is not integrable. So in the Lebesgue sense, the gradient actually is integrable in a generalized sense of non-absolutely converging integrals. That's a different topic. If you ever heard of something called like the Kurzweil-Henstock integral, these integrals, this different notion of integrability, of integrating, then the gradients are integrable in that sense. In fact, that notion of integration was developed to actually integrate gradients that existed pointwise. So there is stuff you can do, but that's a somewhat different question and a different field actually. But anyway, if you ever heard about things about these generalized notions of integration, that's one of the applications, and actually those generalized notions of integration were developed for that purpose. Back to this. So this is what we're going to prove. So we have this, and we're going to use some of the ideas that we have already touched on. So proof. So recall. Let me double L and recall. If we have a matrix R belonging to rotations, then we have that the cofactor of R is equal to R itself. This was a little identity that we showed, right? This is true in n by n. But note that if we have a matrix A, which is actually inside the two-dimensional conformal matrices, then the same thing is true, because A is equal to lambda times rotation, right? And then the cofactor matrix of A is something that will allow us to extract out this lambda, because the cofactor matrix we just get from, I could write it out maybe, but put it over here. So the cofactor matrix of lambda times this rotation, cos theta minus sine theta, cos theta, right? We get by deleting whatever entry and then taking the guy on the opposite side, right? So then this is equal to, let's just write it out. So this is equal to lambda cosine of theta. This guy, we're going to delete this guy, is going to be minus lambda sine of theta. This will be lambda times sine of theta. We take this guy, we delete it, we just have this, but then it's times minus 1 because this is the 2-1 entry, so we get this. And then we get this. So the reason this is working is that when we take the cofactor matrix, we're just getting these individual elements. We're not getting these products. If we had products, then we wouldn't be able to pull out this lambda so easily, but we can. In this case, just a fluke of 2 by 2 or convenience of 2 by 2. So this is the same thing as the actual matrix itself. So that's equal to A itself. Yeah. So in this case, it's also true that the cofactor matrix is equal to the matrix. This is absolutely not true when we take higher dimensions, because this little thing won't work, because the cofactor matrix is not so simple, right? That when we do this in higher dimensions, we delete the 1-1 entry, and when we take the subdeterminant of everything else, so we delete the first row and first column, submatrix everything else, and we'll have a product of these lambdas, which we can't pull out as just a linear factor. Yeah? So are you guys all happy that this is true? Yeah? Cool. So that's pretty convenient, because one of the things we did in the special case of Liouville's theorem, when we have the differential inclusion into rotations, was this identity. So recall that this is just always true in any dimension, that if we take the divergence of the cofactor of any matrix, let's write the matrices like dW, then this is equal to 0 for any smooth W from Rn, from omega in Rn, whatever, from omega tilde in Rn to Rn. And I showed you this again in 2 by 2, but this is just generally true. This is a calculation, but it's with multilinear algebra, it's not too difficult, but it's just a true fact. We're only going to use this for 2 by 2, which is something we could just see, and I just showed this to you. So we have this, and we are going to put these components together in a way that we did before. So if we have a smooth, let's call it U tilde, from omega in R2, this time to R2, with the U belonging to the two-dimensional conformal matrices, then we can put these components together, because then we're going to have the divergence like this. We're going to have that 0 is equal to the divergence of the cofactor of the gradient of U tilde, and the cofactor of the gradient U tilde, because of this fact, is the same as the divergence just of the gradient of U tilde, and that is the same as taking the Laplacian of the first coordinate of U tilde, the second coordinate of U tilde, and so on. Well, that's all because we're doing this 2 by 2, right? And this, of course, is meant in the vector sense, so let's just write it, be consistent. So divergence of a matrix is divergence of the first row, divergence of the second row. Yeah? So, just writing it again, we have that each component equals 0, each component is harmonic, right? Actually, let's take this to be smooth. Let's do it C2, so we have two derivatives. And as you guys know, if you have a solution of Laplacian, then it is infinitely differentiable. It's actually analytic. Yeah? Yeah. And its analyticity, is also not that hard. It's because this function u from this property satisfies the mean value property that or u tilde k, I should say, because we're talking about components, satisfies this, that if we take the average around the ball, centered on x, and stuff we talked about, right? This is true. And this is a special case of Cauchy's integral formula, and then analyticity follows in the same way that we can differentiate through the integral and blah, blah, blah. Yeah? Cool. So in the case when we have C2, then this little identity instantly bumps us up into C infinity. Yeah? Yeah. And the ideas behind that are very similar to the way we do this for the proof in complex analysis. In complex analysis, we establish Cauchy-Riemann equations. In Cauchy-Riemann equations, we establish Gauss-Stats theorem that when we integrate around the closed curve, it's equal to 0. Yeah? And then from that, we establish Cauchy integral formula, which is more general than this thing, and then Cauchy integral formula we differentiate through the integral. Yeah? So the ideas are really simple. The ideas are really similar. All right, let's try and move from this into this case when we just have something which is Sobolev. Let's see how we do this. Well, here's a true fact, which I've mentioned before. I should say true theorem, but I'll state more explicitly. Given a function, let's call it G inside a Sobolev space, W1Q, there exists let's say a sequence of functions which are smooth such that we can approximate in the Sobolev norms such that okay, which is a very convenient property for us, and it's not that hard to prove. It's proved by this notion called convolution, and convolution is like a fancy way of taking an average. So if you have an arbitrary LP function, let's call it f, then one of the things we could do to try and regularize f would be just to take its average over a small ball. Like this. And this would be like a kind of smearing out of something, right? If you remember these early computer paint programs, one of the things they offered you was this smear function where you would like draw some lines, whatever, and then you put this like circular thing on top of your lines and you press smear and it like smudges everything out. It's just averaging out the pixel density of what you've got. That's exactly what this is doing. Yeah? And that'll turn something that is got sharp edges into something which is smoother. Yeah? You can do something a little bit more sophisticated than this, which is to take something which is not averaging over strictly a ball, but averaging over a smoothed out ball. So if we take something which is not, so the characteristic function of a ball is something which would be like this, right? If we did it on the line, it would be something like this. Yeah? If we replace this thing by something which doesn't have sharp corners, which does something like this, and we averaged over that thing, then that thing is what we call a convolution. And that turns out to have more convenient properties because we can differentiate through it and not have a problem with the corners. But morally, it's exactly the same thing. It's just it helps technically to not literally average over a ball, but instead replace the ball by something which is a bit smoother. Yeah? So I will get into this about how this works if I have time after stating this stuff. But all you need to know for the time being is that this is a true fact for this reason, that we can smudge things out with this kind of procedure, and having smudged things out will produce a sequence which is smooth but will converge more and more strongly in the Sobolev norm to our limit. Okay? Some of you already know this theorem, but some of you are fairly new to this. Another thing I want to say to make Sobolev spaces seem more natural is that another true fact. If we take the Sobolev space W1 infinity, which are things which have one weak derivative, but that weak derivative is actually L infinity bounded, then this is exactly the same as Lipschitz mappings. I never remember how to spell this. One way, okay, whatever, Lipschitz mappings. And why so? So if we have a Lipschitz mapping, then for sure it doesn't have pointwise derivatives, right? So what does a Lipschitz mapping do? So we have that f of x minus f of y is less than some constant x minus y, like this. That's what a Lipschitz mapping does. Right? So if we draw the graph of something like this, then the graph will be like this, right? Like the worst thing it can do is something like this. Maybe it's smooth sometimes, but it's allowed to have corners. Yeah, but what it's not allowed to do is to have things that drop too much or raise too much compared to how far we go along, right? So play with this definition of Lipschitz mappings a bit, and you'll convince yourself that this is true. And in particular, if we take the derivative, then just from this, we see the derivative is bounded by this constant c, yeah? Wherever the derivative exists. But the derivative doesn't have to exist everywhere, right? So, I mean, look, f of x being absolute value of x, this is a perfectly good Lipschitz mapping, right? But it definitely doesn't have derivative at 0, yeah? And we can have this as have as many corners as we like. So Lipschitz functions don't have derivatives everywhere, but they do have derivatives almost everywhere, which is a very nice theorem from way back in the day, Rakamattis theorem. Yeah? So if you are not feeling too happy with this notion of Sobolev mappings, you can take the special case. We're always going to do this inside bounded domains. So the higher p is controlling the lower p. So Lipschitz mappings will be a special case of whatever Sobolev mapping we're interested in. Yeah? So if you're not happy with Sobolev mappings, just think about Lipschitz mappings. Yeah? And the key point about this is that we don't have derivatives everywhere, but we do have almost everywhere. Cool. All right. So with these things, our goal now, well, this was just, no, you need regularity of the boundary. Yeah, I didn't want to get too much into it, but yeah, you need regularity of the boundary, because this thing requires a bit of space to actually define this smoothing operation. So if you can construct an incredibly crazy thing where you can construct a set with an incredibly crazy boundary, so that if you consider the interior of, I mean, I can't draw it because it's so crazy, but you can construct a set so that no matter how small a ball you take, then all the points which are at the center of the ball, which you can fit inside a domain, you can construct a set so bad that those points are just a strict subset of all of the other points. And then you just can't define this for most of the set. If you have something which is like a Lipschitz boundary, then you're fine. You can get as close to it as you like. But yeah, you need regularity of the boundary for this to be true. Yeah, absolutely.
Okay.
So I sneakily didn't put anything here to avoid discussing the boundary, but yeah, you called me out, so let's do this. If boundary of omega is nice, whatever that means. Yeah. All right. Everybody happy? Yeah? Cool. So for our purposes, we're going to take something with nice boundary. If we have nice boundary, then this isn't a problem, right? As you can see. So we are going to use these facts, and we're going to show that we actually have something that satisfies the harmonic equation weakly. So what does that mean? So definition. Let's maybe put boxes around this thing. So if function, let's say h is harmonic, then the Laplacian of h equals 0, right, in the pointwise sense. So if, let's say it's harmonic on omega, again, omega will be something with nice boundary. Then take phi, which is compactly supported in this, which is C infinity. Then it's obviously true that we have this. Because this function is pointwise equal to 0. But then we can integrate by parts, and then this is the same as this thing. Like this, yeah? Yeah? All right, so we have this is true, right? And we've seen this before, right? So we just, are you all happy with this, or shall I explain it again? Thumbs up if you're happy with this. Oh, I'm already over time, damn it. Because when you take the divergence of just the gradient of h times phi, then we just apply the divergence to each coordinate, and when you have Laplacian of h times phi plus this times this, and then when we integrate this vector field, then this thing is equal to 0 just by the divergence theorem. Yeah? So then this is true. Yeah? Cool. So that is a true fact, and we'll say that a function, let's call it h tilde, is weakly harmonic if and only if this is true, that whenever we take this thing, h tilde dot product, this test function, dx, then it is equal to 0 for all phi belonging to compactly support like this. So if it's classically harmonic, then it's obviously true, right? Yeah. So I should say we're going to do this, and then this is equal to 0 because this is equal to 0. Yeah. And we say it's weakly harmonic if we ask that this is true. Yeah. So it's a weaker notion of satisfying a PDE, but it is a good notion because we are going to want to solve PDEs where we don't have pointwise derivatives, right? And this thing requires us to have two pointwise derivatives if we want to talk about Laplacian equals to 0. Yeah? But there are going to be situations where we want to talk about a Sobolev function with just one derivative, so in W1p, solving Laplace's equation. And in this formulation, then it does make sense. This in itself makes sense, right? This is a meaningful thing. Yeah, so people have to go. If you have to go, just go. I'm going to complete the statement. Yeah? Are you happy with this? Does this make sense? That this in itself is a meaningful thing. So this makes sense. For H belonging to W1p, right? Just by itself. Yeah? Yeah. And it turns out that this weak notion is strong enough to actually recover pointwise derivatives and analyticity. So this is Weyer's lemma. So I don't know how to spell whale either, and I don't think it's that. Okay. Weyer's, I should say theorem. If H tilde is weakly harmonic, then it's analytic. So we go all the way from having something that is just got one derivative and it satisfies this weak PDE, this weak harmonic equation, this weak Laplace's equation, and then we recover that it's actually analytic, all the derivative exists. And this is actually pretty easy to prove with the right ideas, actually using these convolution ideas. I will sketch the proof next time. So this is one of the tools we're going to use because it allows us to go from having one derivative to gaining all the derivatives. Yeah? So what we're going to do, just to say how this proof is going to go, we are going to use our initial hypothesis that we have the gradient inside the conformal matrices, yeah, to conclude that each coordinate of the gradient is harmonic. Okay, in this weak sense, And that's we can't have anything initially stronger than that because we only have one derivative, so we can't have it actually harmonic. In the original proof, when we had C2, then this little calculation told us it was actually harmonic, right? We don't have that if our hypotheses are that we're in Sobolev space. Yeah? But we're going to use the fact that we can approximate this by a sequence getting closer and closer to it to conclude that we actually have that the coordinates are weakly harmonic in this sense. And then Weyer's lemma will say that the coordinates are all going to be analytic, and that's how this is going to work. Okay? So we're going to put these notions together to conclude this result on Monday. And a really good thing to do if you want to understand these things better is just to use the things I've laid out here, these little these components, and then try and put it together yourself. Try and use these facts to conclude that if we have a Sobolev function whose gradient belongs to conformal matrices, then all these things that we know will allow us this strategy of trying to make something like this work, but we can't actually do this directly because we can't differentiate twice because we only have one derivative. But nevertheless, use these components and try and force the coordinates of your function u to be weakly harmonic in this sense, and then you're done. Okay, and then that would prove it. Give that some thought, see if you can come up with the proof of that, and I'll complete this on Monday. All right, that's it for the day. Have a great day, people. Bye-bye.